Right, we're going to attempt this light question topic sheet. Well, light waves thingy me bobby. Right, ground penetrating radar uses radio waves to detect changes. State the formula linking speed, frequency, wavelength. So learn the actually learn both word and so speed is frequency times wavelength. Speed is wave speed is lambda. Lambda. It's a Greek letter. Equals no silly. Speed is always v. Frequency is f, and then wavelength is lambda. So lambda is wavelength. Let's get that right. V equals f lambda. Right. So we've got a frequency of 170 mega. Right, mega is 10 to the 6 or 1, 2, 3, 4, 5, 6. Kilo is 10 to the 3 or simply 1, 1, 2, 3. Kilo, mega, and you're gonna get giga. If you get giga, it will be 10 times 10 to the power of 9, so it'll be 1 and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's move on. Speed is that. Right, we need to work out the wavelength. Right, so let's start that. So we know speed is 3.0 times 10 to the 8. And then frequency is 170 times 10 to the 6 times wavelength. Then we rearrange this, but we don't solve it just yet. Remember we said in physics they like to see this part. Right, and then the answer is 1.8 meters. So look at this carefully. The original equation substituted, the original equation with the numbers rearranged, and then the answer. Otherwise you lose method marks. You don't want to do that. Right, a radio wave passes through the ground and refracts at the boundary. When you've got a change in density between the two mediums, you get diffraction between rock. So here's the normal. Oh no, let's just do that. Here's the normal. That is called the normal. It is 90 degrees to the boundary. There you go, perpendicular. Okay. So the frequencies changed here. If you can see, these are closer together, higher frequency than these. It's a denser medium. Right, what they're saying. The diagram shows 3 wavefronts before and after diffraction. Yeah, so 1 wavefront, 2 wavefronts, 3 wavefronts. 1 wavefront, 2 wavefront, 3. The same 3. The wave is also reflected at the boundary. So we're expecting this. We're expecting it to bounce, reflect back. Complete the diagram. So what I'm going to do is that distance roughly is that. That should be the same distance, so you show it that way, yeah. They're not going to be closer, further apart, same distance. The wavefronts, yeah, so just remember that these are going to be perpendicular. Parallel to each other, yeah, these are all parallel. So look, these are perpendicular. These are the same distance apart here and here. And the same distance as these are. Right, reflected ray drawn to right of normal and above the rock. Yeah, that's what we've drawn. There's the normal, there's the front, and it's above the rock. Wavefronts are perpendicular to the reflected ray, so that there is the reflected ray, and the wavefronts here are perpendicular at 90 degrees. Wavefronts parallel to each other, they are parallel to each other, and they're the same spacing or consistent with incident wavefronts. So these are the same as these. Right, okay. Explain why, so it's a 3 marker now, explain why the radio waves passing through the rock have a smaller wavelength than the radio waves passing through the soil. How can we say that? Right, first of all, we notice that the wavefronts are closer together. The rock is more dense. It is more dense, optically more dense, or more dense than the soil. So just remember that. When you go from less dense to more dense, the frequency goes higher. Right. So you get a reduction of speed. But remember, the frequency is constant, is the same. So if you reduce speed, so remember V equals F lambda. So frequency stays the same. If you reduce the speed, then the wavelength will go up. No, stop playing. Frequency stays the same, so then the wavelength goes down because V isn't constant, velocity drops. Right, I've got to be careful on that. So reduction of speed, why? Because frequency is constant and V equals F lambda. So basically, if speed goes down, wavelength goes down because frequency stays the same. Right, okay, I've got to get my head around that. So that makes both of us. Right, this question is about optical fibers. Optical fibers use wavelengths for communication. Which of these correct about the statement? Which of these is a correct statement about waves? Right. Waves transfer energy, information, and matter. No, waves do not transfer energy. Do not transfer energy, information, or matter. Nope. Waves transfer energy without transferring Waves transfer energy without transforming information or matter. No, right, okay, I definitely know it's not that and not that. So I'm going to think about that one. Waves transfer energy, information without transferring matter. Yes, they can do. That's why they're using communications. They can transfer information. So it's that one. Right, there you go. Right, a ray of light passes from air into glass. So this is low optical density to higher optical density. Okay. What they're saying, draw the path of the ray of light in air before it passes through. So let's draw that's the normal. Right, so what's happened is the light has come in at this big angle, and because it's gone from less dense to more dense, this angle is smaller. So it has refracted towards the normal, bending towards the normal. So it bends towards the normal. So that's what you can draw. Explain the path of the ray of light as it travels through the optical fiber. This is called refraction. Let's discuss that idea. Refraction. Right, let's get that into. So what we have is refraction is the change in direction of a wave. This normally happens. This is because there, did I write that there? I believe I did that. There is, I was going to say their properties, their densities. This is because there is a change in optical density between the mediums. Right, basically what's happening is you've got a line here, you've got, this is glass, and this is, just say, air. This is less dense. Right, so you have your, right, so it comes in and it's gonna go, let me think about that, it's gonna go, it's gonna go towards the normal. So it's gonna go make this line smaller. So this is big. Just say, for example, 20 degrees. I don't know. Yeah, just make something up. This might be 15 degrees. This is gonna be small. So it's coming that way. So can I do that? Yes, I can. I think that there is That's glass. That's more dense. Okay, let's keep moving on. Remember, this is called refraction. Right. Now, so we need to explain the path. How is it? Why is this being totally internally reflected there, 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 and there? That's the question. So we now need to put an answer to that. Right, so you've got, oh my God, did I just do that? You have total, even if you can write this, you'll get 1 mark. Total internal reflection occurs because the optic, the core has a higher refractive index than air. It has a higher refractive index than air because the angle of incidence is greater than the critical angle. So watch this. This here, this angle here is the angle of incidence. Yeah, so if you've got a normal, here, that angle is bigger than the angle of, than the critical angle. That's where you get total internal reflection. If it was smaller, you'd get leakage out there. But anyway, let's move on. Let's not dilly-dally about. We have not got time to dilly-dally about. Got so much to do, especially with physics. This is a question about reflection. Which diagram shows a light correctly reflected from a mirror? Ooh. There, that's reflection there. That's definitely not true, even I know that. Nope, that's the wrong angle. That should be at the same angle. And in a mirror, it's not going to go through, it should go that way. Okay, that's fair enough. Name the equipment needed to measure the angle of incidence on a ray diagram. This is a protractor. It's a protractor. 1 marker. Ooh, what's going on here? Light from a laser on Earth reflects off special mirrors on the moon. The graph shows the data from a light sensor attached to the laser. First peak shows when the light leaves the laser, and the second peak shows when the light has returned from the moon. Okay, fair enough. Determine the time taken for the light to travel back from the Earth to the moon. So let's get this. So it leaves the laser here. It's reflected off mirror, and then it comes back. Okay. Right. Determine the time taken for the light to travel from the Earth to the moon and back again. Right, it's going to be 1.5 seconds. Yep, it's just simply 3 take away a half. So they want you to 3 take away a half equals 0.5. Fair enough, right? So those are the 2 points. One's at 3, one's at 0.5. Straightforward. Okay, the speed of light is 3 times 10 to the 5 kilometers per second. Calculate the distance traveled by the light from the laser. Speed is distance over time. So the distance, so speed is distance over time. So it's a 2 marker. So they want us to do, how do they want? Okay. Distance, it's only a 2 marker, yeah? So they want speed times time. Speed is 30. 1, 2, 3. So 30,000. No, it says 300. That says 3 and 5 zeros. 1, 2, 3, 4, 5. Okay, times time, which is 2.5, and you should get 750,000 kilometers. Okay, calculate the distance from the Earth to the Moon is half that, because that's double the distance. So it goes from the laser to the Moon and back. We'll do 750. 1, 2, 3 divided by 2 equals 375,000. Right, we'll call it quits there. We'll continue on next time.